Welcome back everyone. In the previous video, we talked about how we can estimate the transformation from one image to another. But have you ever wondered how we can do this seemingly impossible task of morphing one image to the other or warping them in our heads? And we do this with so much ease. How can we enable computers the same superpowers as we possess? In today's episode, we will demystify warping and blending. Let's dive right in. So just as a quick recap, we talked about homography, which is a plane-to-plane transformation, which essentially mimics a three-dimensional transformation in the two-dimensional image plane. So we said, hey, we needed 4 image points, and then we basically, given these correspondences, can estimate the homography between them. If this seems unfamiliar, I would recommend you to watch the previous video and come back to this video because that will help a lot. So what I've been showing you in the previous videos is that I've been warping an image which looks like that to something like this. But in reality, I've been cheating a little bit. What is that cheating, you may ask? I have been technically warping grids which look like this, which are all the same color. Which means that, in other words, I'm warping the raw coordinates from one to the other rather than the colors itself. The question now becomes, because we are trying to warp images, we need to warp colors, right? So let's pick this yellow color pixel and you do the forward warp wherein you apply the transformation, and the pixel ends up somewhere in the middle of the grid of the other image, right? There is no reason that it has to end up at the perfect integer locations of that pixel. Remember that pixels are in integer locations. But when we do the transformation, it could be like 100.1 to 100.2 or something like that. And there's literally no reason for that to exactly end up in the integer location. Okay, so now the question is, how do we handle a scenario like this? What color do we assign to the pixel, right? One simple way is you can say, hey, just pick the nearest one, whichever is the closest one, and you can call it a day and move on. Let's do the same thing for another green color pixel, and you can do the same thing. You can pick the closest one and you can do that, right? This is called forward warping. The question is, how do you distribute color amongst pixels? A better way, rather than just taking the nearest pixel value, is called splatting. So for splatting, what we will do is we'll basically say, hey, this is where the point lies, and I'm going to distribute the colors sort of like based on the distance to the neighboring pixels. And it's sort of like you take a paintbrush and you splotch a amount of paint on the canvas, right? And that's splatting. That's what splatting is. So you can use this thing called the grid data function in Python or MATLAB and implement this. But what's the problem with this stuff? The problem is that you will end up with a lot of holes, which means that like there might be certain parts of the image on the right hand side, the square grid, where you might actually have no pixels there. You might have no colors, which might end up becoming black, right? Instead of it looking smooth like this, you might end up with something like this. So this is generally not that great. So you don't want to use this concept. And we'll see in a few seconds why this might be useful, but in most scenarios, this is not that great. Okay, so how can we fix this, right? That's the question. What we can do instead is, we know that the grid on the right hand side needs to be filled in. We know the colors on the left hand side grid. So what we can do is we can flip this problem around, right? So by flipping the problem around, we say, hey, for every pixel on the right hand side, I can do an inverse warp on the left hand side, and even if the pixel ends up in the middle, I know the colors around it. So I made a very strong assumption when I said I can do this. I want you to pause the video for a second and think about what that is. If you were thinking that, hey, you took an inverse, the inverse is not that easy of a function and it has to be valid, you're absolutely correct, right? I made sure that f inverse exists and it's a mathematically operatable quantity, so I can do this function. Great. So under the scenario where I can invert this transformation, this is very valid. Okay. So for every pixel on the right hand side grid, I basically compute the inverse transformation on the left hand side grid, which is the left hand side grid is also called the source grid. The right hand side grid is also called the destination grid. So for every pixel on the destination grid, I do the inverse warp and get it somewhere in the middle of the source grid. And remember that in the source grid, I have all the colors, right? So even if the pixel ends up in the middle, I can basically take a combination of the colors around it. So let's do that, and you can do the same thing for another color as well, and the same idea holds true. Beautiful. So this is called backward warping. So now how do you actually distribute colors amongst pixels? Remember, we have the neighboring pixels. We will use something called as interpolation. If you're interested in implementing this, you can use the interrupt2 function in Python or MATLAB, and we would get beautiful colors like this. Great. So when would you use either? Almost all the times you would use the inverse warping function, but the only case, more or less the only case you will use the forward warping function is when inversion might not be possible, or it might be too expensive to actually compute that. Beautiful. So let's look at interpolation. Let's zoom into the image on the left hand side. So the star represents where the pixel has ended up after the inverse function, and the other pixel values around it are known. So what you can do is you can compute the distances to each of these pixels, and in the nearest neighbor warping, what we can do is we can pick the closest one and just assign that color. This is quick and dirty and really fast, but the problem is this will give you artifacts in your output image. So a slightly better way of doing this is called the bilinear warping function, wherein you linearly interpolate in both x and y directions, and you basically sum them up, so it will be a smoother transition. With this, coupled with our homography estimates and nice beautiful interpolation and warping, we can actually create virtual billboards like you see in this image. I'm going to play this video where you will see that in different countries where it's telecasted, it's the same exact video, but the billboards are completely made up and it's virtual, and it looks beautiful. And they've also added these artifacts of how it would look like with the actual screen and stuff to make it look very realistic. Okay, beautiful. Now, if you want to sort of use this for panorama stitching or something like that and want to blend the two images together, how would you do that? So one of the simplest methods is called alpha blending. What we would do is we would sort of pretend that, hey, we have this opacity slider in each of the images, and as long as I know how to linearly change the opacity from one image to the other, it will be a smoother blend, right? So one way to do that would basically be to use 50-50%, and it will sort of smooth out the illumination changes as you see on the bottom right image. So one implementational way of doing this is called the alpha blending with center weighting, and this uses a concept called distance transform. So if you Google distance transform MATLAB or distance transform Python, you should be able to implement this with a couple of lines of code. These are great. These are very rudimentary methods and they work fairly well and they're very quick, but they don't really preserve the textural differences of the scene. So a much better method, which is very old, is called the pyramid blending using Laplacian pyramids. So remember from the previous lecture where we talked about scale space. If you have not watched that, I would highly urge you to watch that right now. We built basically spatial pyramids using difference of Gaussians, and we can do something similar to that using Laplacian pyramids. So then what we do is we basically select the common masks, which pixels have to come from left and which pixel has to come from right, and then we do a weighted combination of both of them in the pyramid space. And then we finally go from the pyramid space back to the final blended image. So we have color and texture both blended in beautifully. So as you would see here, in the middle of the image where we are blending the apple to the orange, you'll see the middle part where the apple and the orange blend. You see that you have the texture of the orange and the color of the apple and vice versa, and it looks beautiful and smooth. So there are even better methods wherein we take how heat diffuses in nature, like the heat equation, and we can actually model blending as a heat diffusion problem. And this is called Poisson blending. And this is a very old pivotal paper in the field of blending called Poisson blending from 2003. And I would urge you to highly look at this. This is a beautiful paper. So just to recap, what is warping? When do you use forward warping? When do you use backward warping? How do you interpolate between the pixel values? How do you blend two images together? So I hope the blending has been a wonderful experience for you, and you can really do nice little warping and blending for your images, where you can use this to stitch panoramas together and so on. See you next time. Take care. Bye-bye.